This lecture is part of a series of lectures for Rad229, MRI Signals and Sequences, offered in the Department of Radiology at Stanford University. The 14th lecture on magnetization preparation is divided into two parts. Lecture-14A covers magnetization preparation and fat suppression. The learning objectives for this lecture are to explain the role of magnetization preparation, to draw a sequence showing the magnetization preparation block and acquisition blocks, to compare how different acquisition blocks fit within the magnetization preparation scheme, to explain and compare saturation and inversion for nulling, and to justify why fat suppression is used, and to describe three approaches to fat suppression. Magnetization preparation sequences are used in some cases because the acquisition method may not give the desired contrast. The preparation block may add contrast or change the image in some useful way, and in some cases it adds encoding. MP-RAGE stands for Magnetization Prepared Rapid Acquisition with Gradient Echo, and this is one of the early forms of magnetization prepared sequences. Inversion recovery preparations are used for T1 contrast. Fat saturation is very common, as we'll see in this lecture. T2 preparation is a way to provide T2 contrast in sequences that otherwise may lack this contrast. And diffusion-weighted imaging is very commonly used and will be studied more in detail in the next lecture. So in magnetization preparation, we will have this magprep block followed by an acquisition sequence followed by additional magprep blocks, and we will see this again shortly. Let's review the basic contrast of sequences that we have studied. Spin echo sequences provide proton density T1 and T2 weighting, and these can be seen here. Gradient echo sequences were divided into balanced SSFP, gradient spoiled, and RF spoiled imaging, and provide these different contrasts. In some cases, these are similar to the contrasts provided by spin echo sequences. We use magnetization prepared imaging to provide additional or improved contrasts, or contrasts that can be combined with an acquisition sequence that doesn't have that contrast. We also might use this to do more efficient 3D imaging and to improve the overall efficiency of the acquisition. Let's look at some general considerations for magnetization prepared sequences. We have to think about the frequency with which we play the magnetization preparation, and this is a trade-off between contrast and efficiency. Similarly, we think about the acquisition block length, because the contrast can wear off over time, but fewer blocks will improve the efficiency of the sequence. We have to think about transitions into and out of the acquisition sequence, and the transients that can arise, and whether we need to take special steps to avoid artifacts. We also have to think about whether the magnetization preparation is played for just one slice, or if it can be played for multiple slices that are interleaved. So now we will look at some common acquisition sequences. We want to think about the readout robustness to various effects, such as static field inhomogeneities or flip angle effects. We want to think about the efficiency of the readout and the RF power. We also want to think about transitions between the magnetization preparation and the acquisition sequences, and the effect of signal recovery during the acquisition sequence. So the first acquisition sequence we can think about is a spin echo train. As we've seen, this is robust to static field variations. There's a very simple transition because we can go right from a magnetization preparation right into the echo train. As we've seen before, recovering magnetization will not leak into the signal, so this is a really strong point for spin echo trains. These are moderately time efficient because they're quite fast, although the length of the RF pulses and crushers is longer than gradient echo sequences. These have very good signal efficiency, but a negative is that they might use high RF power during the acquisition. Alternatively, we could use gradient spoiled or RF spoiled sequences. These are still robust to B0, at least with respect to the third sequence that we'll look at. There may be some oscillation as we transition into the sequence. There also may be some recovery of the magnetization during the sequence, and this results in a loss of contrast from the magnetization preparation. These sequences are generally very fast and time efficient and appropriate for 3D imaging. They have moderate signal efficiency, but they have low RF power, which is an advantage. Finally, it's quite common to use a balanced SSFP readout. A drawback is this is sensitive to the static magnetic field inhomogeneities or B0 variations. Another drawback is that if not controlled, there can be transient oscillations in the signal that can cause artifacts. There also can be some recovery of signal, and we will basically approach the steady state contrast of the sequence. So we have to think about the length of the acquisition block, as with the other sequences. A benefit of balanced SSFP is it is very time efficient and it's very signal efficient. A drawback or possibly an advantage is it has moderate RF power, typically somewhere between spin echo sequences and gradient or RF spoiled sequences. So all of these techniques are quite commonly used in conjunction with magnetization preparation. So let's now look at a very common magnetization preparation, which is that of saturation or inversion nulling. And the goal in general of these sequences is to eliminate the signal from something. It could be a chemical species such as fat or water, where we're trying to suppress one or the other, or it could be from regions of the image, and many more things here. The advantages of suppressing a signal is first that it can often come at minimal cost to the rest of the sequence. So if you've removed a tissue, you can still do a short echo time with the rest of your sequence, as we'll see. Another advantage is if you remove a signal like fat, you can increase the dynamic range for the desired signal. Furthermore, if a tissue like fat is causing artifacts, you can reduce the presence of these artifacts by suppressing the signal that is causing them. Some disadvantages of these approaches are that you are exciting unwanted signal and you're somehow nulling it, but it can come back. And the other disadvantage is some of these schemes can disturb or reduce the desired signal, so that this contrast comes at a cost, perhaps, of signal-to-noise ratio in your desired signal. So let's compare saturation to inversion nulling. In a saturation, what we do is we tip magnetization selectively by 90 degrees and follow this with dephasing. And the aim is to leave the longitudinal magnetization at 0 for all T1s. If we have a variation in either the B0 or the transmit B1, this can leave a non-zero MZ, so this can be undesirable. And these saturations are often spatially or spectrally selective, and we'll see examples of these shortly. An alternative is to do an inversion, where we tip the magnetization 180 degrees and wait for the null point. Notice that these are now based on the T1 time combined with the inversion time. So they can be selective if there are different T1s. You can use adiabatic pulses, which will improve the robustness to variations in the transmit RF field. And these may or may not be frequency or spatially selective as well. And then finally, a combination of these two techniques is also often used. So we might play an inversion pulse followed by a dephaser, for example. Also, because the flip angles may vary, we often want to play the dephaser regardless, and sometimes we will over-tip the 90-degree pulse as well. So here's just a little movie comparing the saturation, where we're going to tip by 90 degrees followed by dephasing, and here you see the target effect on the left. In a 3D view, you see the MZ component on the right, and at the bottom you see the transverse magnetization, which is dephased here, so it should cancel to 0. On the right, you see the target for inversion nulling, where we tip 180 degrees and we wait for the null point, and here the magnetization truly is at 0 if we're successful here. So now we can play movies to see these effects here. So you see the tip and dephasing on the left with some recovery, and on the right you see a full inversion with recovery of the longitudinal component, and we would image at that null point. So these videos just give you a sense of what's going on with that magnetization. Okay? Now we would obviously have to consider the different sequence dynamics while this recovery is taking place. But this gives you an idea of the two different approaches that are often used for nulling tissue. So let's turn now to fat suppression techniques and look at fat in magnetic resonance. So fat is very prominent in the human body. There are numerous types of fat, as seen here. Fat has a short T1, approximately 250 to 400 milliseconds at 1.5 T to 3 T, and it has a moderately long T2, about 80 milliseconds. And this means that the signal can be quite bright because of both fast recovery, but also persistence in T2 weighted imaging. The spectrum of fat, mostly there's a strong peak that's at minus 3.5 parts per million, which is 220 hertz below the water peak at 1.5 T and 440 hertz below the water peak at 3 T. But there are actually multiple peaks, including a peak that actually is about 10% of the fat signal that's right at the water peak. So actually, if you use spectral fat suppression, you should never suppress the fat entirely. So this is actually more complicated than you think, but for most purposes, we're going to assume this single peak at minus 3.5 ppm. So we can see an animation where we have fat and water here, and the effect of this is simply that fat and water are going to precess at different frequencies here. And we can acquire images with fat and water in different phase configurations, as we'll see shortly. So the most common approach to suppress fat is fat saturation. And the block diagram along the top shows the goal here. We excite only the fat, and then we dephase the fat signal, and then we simply continue with our normal sequence. In the second row, you see in the frequency domain, we play a spectrally selective or narrowband pulse that excites just the fat, and that's shown by the orange profile. And then we can go about our normal sequence playing a wider band pulse that would otherwise excite both fat and water. This is a shorter pulse, so we can go about our normal imaging sequence quite efficiently. So this is the approach for fat suppression. This is an example of a breast image, a sagittal breast image here, where fat suppression has failed. And it's kind of interesting to look at the failure modes. So here we have effective fat suppression. Here we have a static field inhomogeneity, and now we're accidentally not suppressing the fat signal, so you see the fat is quite bright. And finally, we can have another case where we accidentally suppress the water signal. So this is sort of how fat suppression can fail, as shown on the right. But it works fairly well, and it's by far the most common technique for suppressing fat in MR. So why do we do fat suppression? This is an example showing fat suppression for contrast. So this is a case with a radial cyst, and it otherwise is iso-intense with bone marrow, which is fatty. Okay, and this is on a proton density weighted scan, and on the right you can see when we suppress the fat, we suppress the bone marrow, so the bone is actually dark. So what you see is the cartilage between the bones in the wrist here, and you see this cyst. So often we want to do fat suppression to enhance the contrast of what we're looking at. Another thing, as I mentioned, is we often want to do fat suppression to reduce artifacts. So for example, fat is displaced with respect to water. This is sometimes referred to as the chemical shift displacement artifact. And the fat can overlap with other tissue, as seen in the wrist here. We have a low readout bandwidth, and the fat is shifted with respect to the water, leading to these quite big black regions between the bone and the cartilage, shown near the arrows. And the cartilage is actually wrapping onto other bone. So one way to avoid this is to simply suppress the fat so it's out of the image. On the far right, we see an EPI example where the effective bandwidth in the phasing codirection is quite low. This results in a huge displacement, and the fat here can shift right on top of the rest of the image. So by using fat suppression, which is very common in EPI, we can avoid this artifact. Another reason to do fat suppression is considering dynamic range. So we have to remember that our digitized signal is quantized. Remember that at the center of K-space, the DC signal is actually much higher when you include fat, because you're basically taking a sum across the image. So you're using up your quantization steps. So the diagram on the left here shows you the total signal and the fat and the water signal. But on the right, if we eliminate the fat, we can actually apply a 4 times higher gain to the water signal and use more quantization steps for the water. And remember that the central case-based signal is where this is mostly a problem here, because this is where the signal is typically highest in the image. Unfortunately, because we're acquiring our images in case space, this quantization applies to case space and not image space. So it's difficult to actually undo the effects otherwise. So this is just an example of a fat-suppressed image on the right versus a non-suppressed image on the left. And it's a very subtle effect, but there are fewer gray levels on the left than there are on the right applied to cartilage. And this may be visible to you. It's quite a subtle effect, but it's a real effect that we have to consider. So how do we play fat suppression in a real sequence? Here is a spin echo train sequence, and we simply add the selective RF pulse with a dephasing gradient at the beginning of the sequence. So it's very, very simple to add to these spin echo sequences. Now we can also add fat suppression to gradient echo sequences, and the most challenging of these is balanced SSFP. So if you recall, with balanced SSFP, we can start the sequence by using this alpha over 2 TR over 2 setup, where we tip the magnetization by half the pulse, and then the steady state will oscillate back and forth by this flip angle alpha. And this actually allows us to do quite efficient fat saturation. So this is one example. These are our coronary artery images here, and you can see the coronary arteries near the heart very clearly here. And it's very important to suppress the fat, because the artery is often embedded in fat here. So in this case, after the cardiac trigger, we play a fat suppression pulse, and then we quickly have to enter the steady state. And we've already shown that balanced SSFP can be quite desirable for imaging the heart, because it has nice flow properties for the blood, and the blood is quite bright. Now another approach that's very elegant is to look at the steady state balanced SSFP sequence. And what you see here is that we play this alpha over 2 after the fat sat on the far right, just like we do on the left. But what's interesting is we play the steady state, and we play a minus alpha over 2 immediately before the fat sat. So what we do is we bring the steady state magnetization back to the longitudinal axis, play the fat sat, and then we go right back into the steady state. And you see these beautiful images here showing no fat sat compared to fat sat, and that the other non-fat tissue is very similar in both images. So we're not disturbing the other signal by playing the fat suppression pulse here. So that's a really nice example of combining a magnetization prep block, in this case FAT-SAT, with a balanced SSFP sequence. So let's look at a review question. So what happens if the FAT-SAT flip angle is not 90 degrees? So the answer here is that the MZ for fat will not be 0, so we'll have a residual fat signal. So now let's look at a question. What if what is this residual signal if the fat-sat flip angle is only 60 degrees? Okay, and the answer here is that you get, it's actually a cosine of 60 degrees, or 0.5 of the fat signal. So you'd be left with half of the fat signal. Now another question, why might you use, say, a 100 degree flip angle for the fat-sat instead of a 90 degree flip angle? And the answer here is that you have T1 recovery between the fat-sat RF and the sequence. So if you give it a little bit more of a tip, you might actually have better nulling of the fat. Okay, and now a really tricky question. How does the fat-sat sensitivity to off-resonance compare to water-only excitation, which we'll see shortly? And the water-only excitation is sometimes referred to as a spectral spatial pulse, because it's both spectrally and spatially selective. Okay, and this is subtle, but the answer is this is actually more sensitive because the fat peak is wider, so we're more likely to miss the fat peak with fat saturation than we are to miss the water peak with water-only excitation. So this is a subtle point. point. Okay, now we're going to take a little step away from magnetization preparation because we're on the topic of fat suppression, which is quite important, and just talk about a few other methods of fat suppression. So this is a water-only excitation, which was referred to in the previous question, and this is also goes by the name of spectral spatial pulses. So this is not really magnetization preparation, but if we look at this, the spectrally selective excitation that we use for fat suppression typically takes about 8 to 12 milliseconds at 1.5 T, or about 4 to 6 milliseconds at 3 T. And this is owing to the fact that we're looking for a bandwidth of about 100 Hertz at 1.5 T, or about 200 Hertz at 3 T. Okay, and the reciprocal of the duration gives you roughly the bandwidth, depending on the selectivity of the pulse. So what we can do instead, though, instead of playing the spectrally selective RF pulse, is we can actually modulate the RF and we can play a slice select gradient. And now what we're doing is using what are called sublobes of the RF pulse, but each one of these is spatially selective. But overall, this pulse follows that same envelope of the spectrally selective pulse here. So this will give us both spectral and spatial selectivity at the cost of being a longer pulse than a standard excitation. So this goes by several names. It can be called a water-only pulse, a spectral spatial pulse, or binomial pulses. And the binomial pulse name refers to the fact that you can simply choose amplitudes 1, 2, 1, or in the case shown here, 1, 3, 3, 1, etc. for these pulses. And as mentioned, these are a little bit more robust to field variations than fat suppression. More robust to B0 variations, because the water peak is narrower than the fat peak, so you're less likely to miss it, and more robust to transmit field inhomogeneities, because if you have a transmit field inhomogeneity, what happens here is you just have a small variation in the flip angle rather than residual fat signal. The other thing with these pulses is that because they are longer, you will have a longer minimum TE than if you play fat saturation pulses. So this brings us to another method of fat suppression, again not a magnetization preparation approach, and this is Dixon-based imaging here. So here we look at our sequence and we have our RF pulse and our signal. Remember, we have fat and water here, which are at different resonance frequencies. So what we can do is we excite our signal and we wait for fat and water to be 180 degrees out of phase. We acquire our signal, then we wait a bit longer and we acquire another signal. And this is where the fat and water are back in phase. Now we can acquire these two signals on the same RF pulse, or in some cases on different RF pulses. But basically now what we have is a fat plus water image and a fat minus water image. So we can simply take the sum of these and the difference, and that will give us the water image and the fat image. Now there has to be some processing to get rid of B0 variations in the background, and there are lots and lots of methods to do this. But this is the basic idea of two-point Dixon imaging. Now there's also a three-point Dixon imaging, which uses a third echo that's typically in phase, and the combination of 3 echoes is used to remove the background variation. A related approach is what's called ideal fat-water separation, and this is basically, again, using fat and water images acquired with different echo times so that fat and water have different relative phases. But here we use a least squares estimation from this to estimate the water and fat image at each pixel. And if you do this, you'll have a longer scan time because these are typically acquired on separate TRs, so with separate RF pulses. So you can have a longer scan time, but they preserve the SNR efficiency. So this is really nice because you get the benefit of the longer scan time here. And like the Dixon techniques, we use a post-processing that can correct for large variations in the static magnetic field. And in fact, these techniques are some of the most robust ways to separate water and fat in the presence of large static magnetic field inhomogeneities. So this brings us to our summary of magnetization preparation and fat suppression. So magnetization preparation is used to modify the contrast prior to an imaging sequence. We can pair the magnetization preparation with different types of efficient acquisitions. We can do saturations as well as inversions to null different signals, and we'll see examples in the next lecture. And then we looked at some fat suppression methods. These included fat saturation, where we remove the fat using a saturation. We do water-only excitation, where we simply do not excite the fat, but rather excite only the water signal. And we looked at Dixon techniques, where we use multiple echo times and the combination of these to separate water and fat into different images. So in the next lecture, we will look at what are some other examples of magnetization preparation using some of these techniques that you've seen already.